Okay. Hello, everyone. Thank you for joining today's webinar. My name is Chingwen. I'm Technical Applications Specialist, Dolomite. So this webinar is one of the webinar series we call Microfluidics 101 with Dolomite. So this will be delivered every last Thursday of each month along 2021. So as we have learned about the last section about the PLGA synthesis of PLGA microparticles and nanoparticles by using the Dolomite systems. So today the topic we will focus about how to encapsulate API and drugs in PLGA microparticles using the Dolomite system. So the content today we will talk about including the introduction, the API drug encapsulations, multiple emulsions, and the second method for API in drug encapsulation is direct powder encapsulations, and the third method is PLGA nanoparticle encapsulation, and finally the conclusions. So today the webinar will be including the two parts. So the first part we will start with the presentation, and the second part will be Q&A section. So if you have any question, just feel free to write out the question in the question box. So I will try to deal directly to you during the Q&A section. So let's start with the presentation. So as we have learned about in the last session about the microparticle PLGAs. So PLGA is widely used for micro encapsulation and controls the release API, protein, and antigens, and is recognized as a safe by FDA because using the traditional method for hydrophilic drug loading are poor as low drug loading, and also is produce a polydispersed particle with hinders accurate drug release. So using microfluidic methods, we can achieve high drug encapsulation efficiency and also high monodispersity. The particles, microparticle PLGA were is produced by using the micromixing emulsification method. So in this case, PLGA dissolved into an organic solvent with low water miscibility like DCM, and droplets are formed at the microfluidic junctions. And for this method, droplet size controls by the selecting junction size and just adjusting relative flow rate of the continuous and droplet phase. Finally, the PLGA microparticles, so these monodispersed particles, will occur as results of the solvent extraction and evaporization, as you can see in here. And for this method, the API encapsulation, the API is always brought in using droplet phase. And for PLGA nanoparticles, it was synthesized by using the hydrodynamic flow focusing method. So in this method, the polymer particles form using process of the nucleation and grow, and polymers will dissolve in the solvent, typically is the acetate, and it crossing out by fast mixing with the anti-solvents. We use waters, and we contain a surfactant to stabilize particles against agglomeration. And for this method, the particle size is controlled by just adjusting flow rate ratios of the polymer and aqueous solution. For encapsulation of API or drug, for this method, the API can be brought in both continuous phase in case of the hydrophilic APIs, or droplet phase in case of the hydrophobic API. Here is our single channel system, microfluidic single channel system, which mostly used for R&D lab scale purpose. So it will include the 3 pressure pump, the microfluidic chip, and microscope. So the microfluidic chip will be connected with the pressure pump through the tubing and is located under the microscope. We integrate with high-speed camera to visualize all the process which happened inside the microfluidic chip. And all of the parameters and process conditions can be controlled from using our software from the laptop or computer. This is a flexible system, so it can be used for many applications. So depending on different application, we can choose a different type of the chip geometry. For scale-up system, we have a TELOS. So the TELOS system increases the throughput in 3 distinct ways. So the first is increase the flow rate through the individual junctions. And the second is the increased number of junctions working in parallel. So for the TELOS microfluidic chip, we have 7 channel junctions integrated in 1 chip, so it can work in parallel. And the third way is increase the number of chips working in parallel. So for the TELOS system, we can operate up to 10 modulars or 10 chips working in parallel. So it can increase the production rates up to 70 times compared to single channel chip. So for example, 1 TELOS clamp modules, as you can see in here, it can allow typically flow output of the 3 ml per minute droplet from 1 microfluidic chip. So if we scale up to 10 clamp modules working together, it would increase flow output up to 30 ml per minute, around 2 liters per hour. So we will talk more about the first method for API drug encapsulation. It's multiple emulsion. So with this method, with the PLGA cell microparticle production, we will provide. So we will use 2 types of chip in this application. So the first chip, we call it chip 1, is a small droplet chip to create a small droplet. And using the second chip to generate the multiple emulsion droplet, we have bigger chip junction size. So normally, the API is pre-dissolved in the aqueous medium and fed to the chip 1 to generate the small water in PLGA, the DCM emulsion. So the water will contain the encapsulant or API drug inside, and it will disperse in PLGA in DCM. And after that, the primary emulsion which form in the chip 1 will be is fed to the chip 2. So the chip 2 normally have a larger chip junction size to be able to create the larger droplet which contain the small droplet inside. So in this case, we will generate the water and PLGA and DCM in upward phase emulsion. So the multiple emulsion we work through the solvent extraction like the PLGA microparticles generation processes. Thus, we have learned in the previous sections. So it will leave the water droplet in PLGA matrix. So final product will be including the PLGA microparticle with encapsulate of the water and API or drug inside. This slide showing the multiple emulsion setup. So we use the 2 type chip in here. So the chip 1 will be generated the small droplet, and we connect to the two pumps which provide the fluid of the water line and API, and the second pump will be connect with the outer phase which provide the PLGA line. So normally we use a different small droplet chip size to be able to generate the different small droplet size. So basically we typically we use the 5 micron chip junction or 14 micron chip junction for the first chip, and product after formation in the chip 1 will be fed to the chip 2. So chip 2 typically is the 100 micrometer chip junction size with a 3D flow focusing geometry. So it will be able to generate from 50 to 100 micrometer of the droplet. So for this one, we will be able to create the multiple emulsion inside one each droplet PLGA with dispersed in upward phase. Here, showing some results using 3D 100 micrometer flow focusing chip. So in this application, we use 2 different chip junction size of the chip 1. So first we use the 14 micrometers chip junction size chip 1 to generate the 14 micrometer inlet droplet here, and the second chip experiment we use the smallest chip junction size like 5 micron chip junction size to generate a 3 micron inlet droplet here, and using 3D 100 micrometer flow focusing chip, we generate successfully the 50 micron PLGA droplet which contain different inner droplet inside 14 and 3 micrometer. So as you can see from the microscope images, so it's showing very monodispersed the interface inside, and very monodispersed as well as a monodispersed of the PLGA microparticle droplet by using this method. So the results are the high monodispersity with both primaries and secondaries emulsion, and we obtain the precise controls over the number and dimension of the inner droplet. So by controlling the chip junction size of the inner, the first chip to generate the different inner droplet size, and it also precise controls over PLGA shell thickness. So by just changing the relative ratio between the droplet phase and continuous phase, we can generate the different particle, different droplet size of PLGA. So it will generate a different the PLGA shell thickness depending on the content of the PLGA amount in each droplet. And finally is the precise control over the amount of aqueous phase encapsulated by just changing the flow rate ratio of the droplet, so we can encapsulate more or less water inside of the PLGA microparticles. So next we will move to the second method for API or drug encapsulation is the direct powders encapsulation. So for the direct powder encapsulation, only one chip is used for this methodologies. So typically we use 100 micrometer chip junction size. So in this case, the hydrophilic powders API or drug will be suspended through the PLGA DC emitter, and to make sure it's the mixing well and homogeneous disperse in the PLGA mixture. And after that, so using the hundreds micrometer of droplet chip junction, we will generate the emulsion which contain the API or drug powders inside the PLGA and solvent, and the emulsion will go through a standard drying process to leave the API powder distribute through the PLGA bed. So the setup of this system, it can be shown in here. We have a 3 pump, with the first pump will be deliver the carrier phase fluid. So it will be connected to the outer channels, outer line channels of the microfluidic chip. And the second pump is the droplet phase, which contain the polymer PLGAs and API and solvents like DCM. So it will pump to the inner chip channels or droplet chip channels in here. And the third pump is the optional, which is full for wash fluids using water to flushing or primarily cleaning of, before and after the running experiment. So this one shows how the process happened inside the microfluidic chip under microscope. So in here we will have a droplet phase, the polymer API and solvent will be in here, and the container phase, the carrier is the aqueous phase, or waters, which including the surfactant, and the emulsions will be generated after passing of the chip junction, and after that dry processing will be take over and generate the API powder distribute to PLGA bed. Here showing some results with this method. So it's highly efficient drug encapsulation. So we obtain from 60 to 95% encapsulation efficiencies, and it also high process reproducibility. So by using the microfluidic, it's very easy to control the parameter like flow rate. So it's very reproducible to generate the PLGA encapsulated microparticles. And the even distribution of API within a bit can be obtained. So if you see in this image is the fluorescence light excitation, the image with API encapsulated inside the PLGA bit. So we can see it very even distribute on with in the PLGA microparticles. And also its high particle monodispersity, you can see from CM image in here, is very monodispersed of the microparticle PLGAs. And also it's very easy to control over drug loading by just controls the content of the drug encapsulate inside PLGA particle, and high control over the risk profiles by just controls the different microparticle size as well. And last method we talk about today is encapsulation of API and drug in PLGA nanoparticles. So normally, as we mentioned in previous section, we can generate the nanoparticles by using the hydrodynamic flow focusing method using the 5-input chip and 3D flow focusing chip. So for 5-input chip, so API already API can be encapsulated inside the nanoparticle PLGA by just brown into the both continuous phase or droplet phase based on different properties, wetting properties of the API or drug. So in this methods, we use a different method to generate the PLGA nanoparticles with encapsulate the API inside. So the setup will be using in this method is 100 micrometer of 3D pore hydrophobic chip, and the concentration of the PLGA in this case is used in range of the 0.5 to 2% weight percent, and for this method, the API will be dissolved in the aqueous carrier. So since it's a hydrophilic API, so we can dissolve or disperse in the aqueous phase. So the aqueous phase polymer solution, and we use the fluoride phase pumping together in chip junction to create the laminars or mixing stream between the two polymer solution and aqueous phase. So in this case, the work reactor is a hydrophobic property, so it's protect from the precipitation of the polymer particles by water invisible emulsion stabilizer. We call it fluoride phase. So fluoride phase is used in this case to coat the wall of reactors. So it will prevent the excess of by the polymers, the particles after polymer nanoparticle generation. Here is showing the PLGA nanoparticle setup. So in this case, we use the 3 to 4 pump for delivers of different fluid into the chip. So the first is a fluoride phase, which will be connected to the one of the outer channel of the microfluidic. You can see in here, and the other aqueous phase with continuous phase will be connected to the other outer phase of the microfluidic chip. You can see in here, and the third pump will be organic droplet phase, which contains the PLGA and the solvent. So normally we use acetone in this case. So it will be pumped, we will connect to the droplet light or the inner light channels of microfluidic. You can see it here. So when we pumping together into the chip junction side, it will be generated of the flow focusing the mixing stream between the two phase, the aqueous phase and organic droplet phase, and finally the fluid phase just for the coating of the wall channel. So it will, the nanoparticle will be generated after passing, after the mixing through the microfluidic chip junction and flushing out to the reservoirs. So the fourth pump is recommended to you in this case to be able to do wash at the wash phase. So it will be used before and after for flushing or cleaning the before and after the experiment, running experiment to protect the chip and tubing, always cleaning after finished experiment or before running experiment. Here showing some results of this method. So we achieve the stable formation of polymer particle, PLGA particle. So the PLGA particle will produce continuously with no intervention for a period of 5 hours. And during the final production period of the PLGA solution flow rate was set to 50 microliter per minute. And the particle size is successfully controls in the region of from 40 nanometer to 800 nanometer by changing the relative flow rate of the polymer solution and aqueous phase. So the conclusion, the methodologies for fabrication of stable PLGA microparticle and nanoparticle formulation have been demonstrated to encapsulate of the hydrophilic API. And for Dolomite equipment, it can be successfully used to produce whole-cell polymeric microparticles that can find many applications in many different areas. For example, like hydrophilic drug encapsulation, or even though we can apply in food or cosmetics, or more and more. And the particle size was successfully controlled in a region of from 50 nanometer up to 30 micrometers by using different method and different microfluidic chip. And in each case of the microfluidic, it enables to reliable API encapsulation in PLGA particles. And Dolomite processes can be scaled up to pilot plant production levels by using the multiple modular tailored system. Okay, so I finished the presentation today. Thank you for your attention. And now we will move to the online Q&A section. So if you have any question, please write down the question in the question box. So I will try to answer directly to you through the Q&A section. So now, please write down your question in here. Otherwise, if you don't have any question from now, maybe you can have question later. So you can send the question directly to the emails Hanoi office at blackshade.com. So I will try to delete all of the question through the email as well. Okay, I got one question. Is it possible to test this technique for enzyme microencapsulation, the protein side matters? Okay, so yeah, actually, for it's right, you are right. So it's possible to use this technique for enzyme microencapsulation as well in PLGAs. So the protein inside it doesn't quite matter for this case. If you have a protein size big, so you can encapsulate in big size of micro PLGA particles, bigger size. So if you have small or you want to encapsulate in nano size, so you must to have a very small in nano size the protein or encapsulant. So normally for enzyme microencapsulation, so you can disperse the enzyme in the aqueous phase and no. So for in aqueous phase and do the multiple emulsion, or you can disperse making it emulsion or suspension actually from the interface in PLGA and the solvent, and after that encapsulate in PLGA microparticles. I hope this helped. And the next question. Okay, I missed the beginning unfortunately. So can you please elaborate on the intended application of this technology? Is suitable for oral delivery of the drug? Yes, actually. So we will record these webinars again and we'll published on our the channels, YouTube channels, and we'll send to you. So hope that you can see all of the presentations later. However, so for this one, yes, it's suitable for oral delivery drug. So normally yes. So it's normally we can for this application we can encapsulate the hydrophobic and hydrophilic both inside the PLGA microparticles, and we can make the microparticles, the PLGA, and encapsulate the drug inside the microparticles, and from that we can use this one to make up the drug with oral drug delivery, of course. Okay, yes, thank you. So basically for protein microencapsulation, as I know, so that many customers who are already studying about the encapsulate of the protein and enzyme, or even though with the ADN materials into the PLGA microparticle by using the encapsulation method. So mostly we have two. We can use the two methods for encapsulation, as I already mentioned in this presentation. So first, you can disperse in aqueous phase and making multiple emulsion with encapsulate the water and enzyme or the protein material inside the PLGA bit, or the other way you can disperse in together in DCM and PLGA to make up suspension and just pass through the tip junction to create the droplet. So during the dry process, you can encapsulate the protein or enzyme inside the PLGA microparticles. Okay, good question. What the fluorophase from wind farm? Yeah, the fluorophase actually is one of our product. It's our chemicals. So that is including the stabilizers, emulsions with compatible with the biomaterials, and it can protect the droplet agglomeration during after the droplet formation. So it have a role like a surfactant, but it's biocompatible. So if you have more interacting on this fluorophase product, you can visit to our website, Dolomite Microfluidics.com. So you can get more further details about the fluorophase component. So otherwise, I can send you the more detail about the component or the product of the fluorophase after the meeting through the email. The next question is, can the equipment use other polymer beside PLGA? Yes. As I already mentioned in many previous sections, that our equipment, our product is very flexible, so it could be used to generate the microparticles, different type of microparticles, and we use a different many application. For example, like agarose or alginase microbead, or even though with gen diffusion or the polymer beads, some polymer beads like PMMAs, for example, as well. So it's very flexible for application. So with the different applications, you just using the different chip geometry and different materials, so you can achieve the different type of the particles. Hope it helps. Okay, next question. Hi, I'm in Australia, and you mentioned the emulsions webinar for today would be started at 14 ET time. Why, when I'm looking now, it got to finish. When you are going to repeat it? Okay, so we will record. We already recorded the webinars, so we will put it after separate date, and we'll email directly to you to let you know it's already online later. So it would be within 2 days. I have some question regarding encapsulating small molecules that has acidic nature in PLGAs. Yes, please. How can I make sure that small molecule is not going to be released during the processes? Yeah, good question. So normally using okay, so process of the making spheres. So it's a good question, right? So normally with the acidic nature molecule, the acidic nature in PLGA, so we can calculate. We do not know during the process running, but we can calculate the encapsulation efficiencies as a post analysis of the process. So after finish your encapsulation, you can do the calculation of encapsulation efficiency. So if the so you can know how much of the materials released during the process of making sphere. So do you have any idea regarding accelerating the process? So it's really long time to make 1 mil for 4 hours. You're right. So normally using with the microfluidic droplet, so not for too high production rate using the microfluidic method. So for first the IND scale, 1 mil for 4 hours. So it would, after 4 hours, it would be finished also the process of the solvent extraction or solvent evaporation. So finally, product US after 4 hours, it should be including the PLGA microparticle, which contain your encapsulant inside. So after that, I think the only way you just need to do is to analyze with the post-analysis methods to calculate encapsulation efficiency to know how much the molecule is going to be released during the process. We are not sure that during the process we are not much sure that the molecule is going to release. Normally using with the surfactant during the droplet generation. So depending on type of the surfactant, it will prevent the different type of the linking. So it will be able to have different type of the process, the cross, we call it cross linking, across leaching, releasing the process during the experiment. So so it depends, really depending on the surfactant using as well. But anyway, yeah, very good question. I will try to find out more the information about this process, and we'll be able to email you later with the more detailed answer. Okay, you're welcome. Yeah, sure. Yes. So, do you have any more questions? Otherwise, you can just email me from to the Hanoi office at PLGA.com. So we will answer you on the question through the emails later. And also, I have just announced that for next webinars, it will be the last Thursday of next month. So the topic will be focused on how to generate the lipid and liposome nanoparticles by using the Dolomite system. So if you have interesting on that topic, please go to our website and make a registration. If you have no more question in here, or you have a question further later, so remember that just please just email us to hanoiofit@PLGA.com. So we are happy to answer all of your questions through the email. So if no more questions, I would like to close today's webinars, and I hope all of you enjoyed the webinars, and hope that we can see all of you later in next webinars. Thank you very much. Thanks.